This lecture is going to be on air tubes and the standing waves that are created in an air tube. Okay, our objectives in this set of PowerPoints is to understand that resonance occurs in air tubes. Okay, that's what a lot of our wind and brass instruments are. The flute, the clarinet, the trumpet, the trombone. These are all examples of air tubes. Okay, so we're going to need to be able to draw and interpret wave diagrams associated with these air tubes and differentiate between the two types of tubes that we'll be studying. A tube that's open on both sides, which we call an open tube, and an open-closed tube where one side is open and the other side is closed. Okay, and then we're going to introduce you to a couple of the wavelength formulas associated with the air tubes. Okay, first off, we need to recall that sound is a wave, okay? It's a longitudinal wave going through the medium of air, okay? Or almost any other substance. It does require a medium. Sound does not travel through a vacuum, okay? And what happens is that the air molecules move back and forth, okay, being compressed and stretched at the same time. And what they do is they hit the next molecule and the next molecule after that and so on and so on. And that's how the sound propagates from the source of the sound to whatever we actually hear. Okay, and instead of talking about crests and troughs, okay, for a longitudinal wave, we don't really talk about crests and troughs. Instead, what we talk about are compression zones, where the molecules are compressed together, okay, they're really, really close together. And then we have rarefaction zones, okay, areas where the molecules are stretched apart. There's a lot of room in between them. Although I make the analogy to crests and troughs associated with compression and rarefaction, they actually correspond to the equilibrium points. One is a downward traveling equilibrium, okay, and that would be the compression zone. And the rarefaction zone would correspond to the upward traveling equilibrium. Okay. And the speed of sound is going to depend on air pressure and temperature. In the next set of slides, we'll also see how it varies with solids and liquids. But in general, we use a number somewhere around 340 meters per second for the speed of sound in air. Okay, and that's pretty good as long as we're talking STP and roughly room temperature. Okay, so I told you about wind instruments, okay, and what wind instruments do to create the sound is they create standing waves with the frequency corresponding to the various note. Okay, changing the length of the instrument, which corresponds to most brass instruments, or establishing nodes and antinodes, which is what reeds and woodwinds do, okay, changes the first harmonic or changes the fundamental frequency that we are playing. Okay, and that's how we are able to get the different notes that the instrument provides. There's a little bit also being done in your in the mouth and how you blow to change the note, but for us, our purposes, we're just focusing on the length of the instrument. Okay. First off, air tubes have two different types. Okay, a tube that is open on both ends. Okay, you can think of a flute as being an instrument that's open on both ends. You're blowing in one end and the other end of the tube is open. Okay, in that case, open ends of any kind of air tube is going to act as an antinode. So the ends of that tube must be an antinode. For strings, when the string was tied down on both sides, okay, the end of the string had to have been nodes. The string was not able to move at all. For air tubes, okay, the air is free to move pretty freely because there's nothing blocking it. Okay, that forces the ends of the tube to be antinodes. And by structure, you must have a node in the middle. Otherwise, you're just blowing air straight through it. And then you're not going to get a note. There's no resonance associated with that. You have to have a wave. Okay, so in this picture, what we have is the air associated with the wave associated with the first harmonic, second harmonic, and third harmonic. Okay, if you look at this, the first harmonic doesn't really have an eye. What it has is two half eyes. And then the second harmonic has one and two half eyes. Okay, mathematically, it's pretty much the same as a string. Okay, in the first one, I have one full I. In the second one, two full I's, and then three full I's, etc., etc. But it's important to know that a half an I corresponds to only a quarter of a wavelength. Okay, so in terms of a wavelength, okay, we're going to need to uh, just focus on the fact that here's a quarter of a wavelength right here, okay, and then it comes back to half, and that's a half a wavelength, and then we have the remainder of this wave. Okay, so half an I only corresponds to a quarter of a wavelength. Okay, and these are the diagrams associated with the first, second, and third harmonic. You can extrapolate for the remaining harmonics. Okay, the other tube that we're going to encounter is an air tube that is closed on one end. This is what you get when you blow across the top of a bottle and you hear a sound, for instance. Okay, and what happened in a clarinet is another example. Okay, you're blowing in one end, but really your lips are closing that section off, and you're just creating small vibrations there. Okay, but in the case of an air tube that's closed on one end, okay, that end has to be a node, okay, because the air isn't free to move on that end. Okay, it hits a wall and pretty much stops. So that's going to be a node. There's no movement of the air molecules. The open end is still going to be represented as an antinode. Okay, so this is the first three frequencies that I'm going to hear for an air tube. Okay, notice that I said the word frequency and not harmonic. Okay, because if I look at these diagrams, especially that first diagram, I do not have even half an I in there. I mean, I only have half an I. I don't have a full I. Okay, that's only 1/4 of a wavelength represented there. The next one down, I have 3/4 of a wavelength, and then 5/4 of a wavelength. Okay, if you can see the progression, I go from 1/4 to 3/4 to 5/4. You can pretty much guess what the next one would be, 7/4. Okay, so what I'm seeing is a progression of just the odd number on top of this fraction. Okay, and that's the reason that I don't say the first three harmonics, okay, because these are only the odd harmonics. Okay, an air tube that is closed on one end will only have odd harmonics. There will be no even harmonics. So this is the first, the third, and the fifth harmonic. So just to summarize, okay, anytime you encounter a closed end, okay, part of the instrument that the air can't move or the string can't move, that must be a node. Okay, open ends where the air is free to move or perhaps the string is free to move, that's going to be represented as an antinode. Okay, and the first harmonic, or synonymous with that, the fundamental frequency, okay, is still the longest wavelength that matches those rules. Okay, so the frequency will give me the wavelength, and the wavelength must fit in that pipe or string. Okay. So the open harmonics, okay. In this case, the loop diagrams look a little bit different, but really they're just the same things except inverted. Okay, it's kind of like sine versus cosine. If you look at them long enough, there's really no difference. Okay, and so I have the same formula that says my wavelength is going to be 2 times L divided by the nth harmonic. Okay, and my nth harmonic is going to be n times the first harmonic. Okay, it shouldn't say 0 there. It really should say the number 1. I'll need to update that. Okay, so the nth harmonic is n times the first harmonic, and that's what I have on an open air tube. Okay, for an open closed air tube, okay, I'm only going to have the odd harmonics. Okay, so that's where people are going to get tripped up a little. Okay, I may ask a question, what is the second harmonic associated with this open closed air tube? And A would be like 100, and then 200, 300, 400, and then E would be none of the above. And this would be one of those none of the above cases. There is no second harmonic associated with an open closed air tube. Okay, so this is the formula, okay? Remember, it was 1 over 4, and then 3 over 4, and then 5 over 4. So that's where this first formula says the length of the tube, okay, is going to equal n times lambda over 4, and where n must be an odd integer. Okay, so my wavelength, okay, lambda for the nth harmonic, is flip that around, is going to be 4 times the length divided by n. What that means is my first harmonic is going to be 4 times the length of this tube now. Okay, and my frequency formula, okay, is pretty much the same frequency formula, but there's an extra requirement, okay, that n must be odd. Okay, thank you.